If you had two LANs, LAN 1 and LAN 2, and LAN 1 has 100 computers on it, and LAN 2 has 50, and you need to connect them together using these two routers, and you were given a prefix of 123.246.10.0/24, and you needed to number your network so that it would function, you would need to know how to subnet this. That's what we're going to learn about. We're going to learn about subnetting. You could take this /24 as it is, as it's been given to you, and you could assign it to this LAN over here and have plenty of address space, okay? But that wouldn't solve the overall task. You need 3 subnets. A router always has discrete subnets on every interface. So this router has 2 interfaces. So you can say this is subnet number 1. Over 2. Subnet number 1. This is subnet number 2 in here. This is subnet number 1. This is subnet number 2. And this is subnet number 3. All right? The routers share this subnet, but it's still a subnet. So you need 3 subnets. You have 1. You could, like I said, you could use this whole thing somewhere, but you need 3. So subnetting is an exercise or an effort of repurposing what are previously known as host bits for network usage. So what do I mean by that? Well, let's put our scenario aside for a moment, and we will remember that we need 3 subnets, and we know what size they are. And so this 24 means the mask is 24 binary digits across of contiguous binary ones. An IP address is 32 bits across, okay? 32 bits. What is bits? Bits comes from the phrase binary digit. So the B, the I, and the T form the term bit. That's where we get the word bit, binary digit. The first 2 letters of the first word bi is sort of like bicycle. A bicycle has 2 wheels. Well, binary is a numbering system of 2 numbers, a 0 and a 1. Okay? So this 32 binary digit string, I'll mention quickly that IP addresses are in decimal notation. They're in human recognizable form of decimal notation. That's how we understand IP addresses as people. And that's what this is called. This is dotted decimal notation, or dotted quad is another way of referring to an IP version 4 address. And it's in decimal form. Well, computers, as they look at IP packets flowing across a network, they look in the header of an IP packet and they see the IP address, but they interpret it as binary. So this is really a 32-bit binary string. We will get comfortable with converting decimal to binary, not because we want to think like computers, but because we want to learn how to subnet. And that's what we're talking about in this video, is how to subnet. Well, why do we need to convert it to binary? Because when you start looking at subnetting inside of one of these groupings, you will come to understand that it is much more logical to look at how to subnet when you're looking at it at a binary level. Okay? So you'll see what I'm talking about. Now, this mask is a contiguous string of ones. That's what a network mask is, or a subnet mask. The ones start on the far left, and it's just 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8 dot 0. So these groupings of IP address and mask, this is the mask, by the way. These groupings are 8 binary digit groupings. 8 plus 8 plus 8 plus 8 is the 32 bits that we understand is an IPv4 address. So the mask is an interpreter that, when applied to the network, tells you which bits are defined as network bits and which aren't network bits. What is a bit that's not a network bit? It's known as a host bit. So here's the delineator on the 24th binary digit boundary, because whoever gave us this prefix says so. This is what they're giving us. And so all the ones over here are known as host bits. So we have 24 network bits and 8 host bits in this assignment. So the opportunity that you have to renumber, or not renumber, but to IP number or IP address your network, where you need 50 addresses here, you need 100 over here, and I'll add real quickly that a router always needs an IP address in order to route IP packets. So you really need 101, because you got to put one there, and you have 100 computers over here. You need a subnet that at least has 2 for the 2 router interfaces, and you need a subnet that at least has 51 for over here. So you need 3 subnets. 1, 2, 3 subnets. The opportunity that you have to accomplish that task is here. That's your opportunity. You have 8 binary digits for which you can repurpose in this direction for subnetting. So again, I may have mentioned it before, I'll say it again. Subnetting is an exercise in sliding this boundary to the right. Subnetting is an exercise in sliding this boundary of 24 to the right, okay? And so when you do that, you're cutting into these 8 binary digits. Yes, you're cutting into this octet. I'll say quickly that these are known as bytes. A byte is 8 bits. So this is a byte. It's made up of 8 bits. Otherwise known as an octet, like an octagon is a shape with 8 sides. An octet is a byte. An octet is 8 binary digits. So this is the first octet, this is the second octet, this is the third octet, and this is the fourth octet. So our focus as we subnet is on the 4th octet. Now, another rule, as you're subnetting, the network bits never change. So to begin with, the first 24 bits we know right away are never going to change. So we know that as we number that network that we had drawn down here in the picture, the first 3 octets are always going to be 123.246.10. Always going to be, for every subnet assignment that we have, is always going to be at least that. As we subnet, we're moving this network boundary over. So now some of those subnets are going to not only be 123.246.10, but it's going to be a portion of these 8 bits here will take on part of the subnet ID. We're going to get into that, and it'll become very clear to you what I'm talking about. So these are some of the rules we're going to go on as we move forward, okay? So let's put this back up here. 1, 2, 3. Excuse me, let me just pause for. Now, as we subnet, again, we're focusing on the 4th octet. In order to dig into subnetting, you got to look at it in binary. I already told you that. And here's how to do it. Blow this up. Blow up that 4th octet and draw a scale. The scale is easy to remember. If you can remember the number 1, you can remember the scale. 1, double it, 2, double it, 4, double it, 8, 16, 32, 64, and 128. These are the 8 binary digits of this 4th octet. They're placeholder values. So any binary digit that falls under one of these placeholders takes on that value. Remember, binary digits are either a 0 or a 1. If it's a 0, there's no value in that space. If it's a 1, then it takes on that placeholder value. I'll show you what I mean. So this is the first bit, the second bit, the third, fourth, fifth, sixth, seventh, and eighth. Okay, so those are the 8 bits of this byte, otherwise known as an octet, but these are the placeholder values that those take on. All right, so as we slide the /24, so again, here's the dot. I'll just draw the dot right here. This is the natural /24 boundary that we got from whoever assigned us this prefix. Just keeping you focused. And our desire is to repurpose one of these host bits as network. Let's slide the mask over 1 space. We're going to slide it over to here. This will now be known as a /25. This now becomes a network bit. We just slid the network bits over and we redefined the boundary, and now these are our host bits for this newly defined /25. A rule in calculating how many addressable hosts that you have on a subnet is 2 to the nth power minus 2. N equals how many host bits you have in a subnet. Well, in this one that we just slid over, we only have 1, 2, 3, 4, 5, 6, 7 host bits. 2 to the 7th power, I like to count it like this. 2, 4, just double. Start with 2. 2, 4, 8, 16, 32, 64, 128. So 2 to the 7th power equals 128. 128 minus 2 equals 126. We have 126 addressable IP addresses in this subnet. Now the reason for the /2, or excuse me, the -2, is because every subnet starts, when you start counting binary, when you start looking at this in binary, you start at 0, a 0 in every placeholder, a binary 0. Okay? The next one, we're just gonna start counting binary. The next one would be like that. I'm putting in equals here because this is going to be what we convert back to decimal. This is binary. This is our binary chart. All this down here, but we're going to convert it back to decimal over here. So I told you a moment ago that when calculating binary to decimal, if there's a binary 1, then you add up that placeholder value when converting it back to decimal. In this first string of binary, there's no 1s, so this would equal 0 in decimal. In this second string of binary, of 0s and 1s, you only have 1. Well, look what placeholder value it takes on. 1. So you add those up, add up all your 1s. Well, there's only 1, and it has a placeholder of 1, so that equals decimal 1. Let's keep counting. By the way, these newly defined network bits, we're going to use 0 for the very first one. Well, guess what? This keeps on carrying down. You never change your network bits when you're looking at your subnet. So we borrowed this 1 bit to have this /25. And so that is now a network bit, and again, it never changes. So as we count through here, we never go over into that column. It always stays 0 all the way down. The next one for host bits would be like that. Is that making sense? I hope it is. When you convert this back to decimal, you add up that binary string of 0s and 1s. Everywhere you have a 1, it takes on that placeholder value in the column heading. Well, in that case, it's a 2. Next one. I think this is going to help when you start having multiple 1s. Well, you might say, well, why did you put 2 1s there? Well, convert those back. Convert it back to decimal. This takes on a placeholder value of 1. This takes on a 2. 1 plus 2 is 3. So there you go. Decimal 0, 1, 2, 3. Next one. This equals 4 because that placeholder is 4. Next one. 4 plus 1 is 5. Do you see what we're doing here? I hope so. And so as we're counting through here, let me just erase some of this because I think you're tracking at this point. If we were to say ditto, kind of ditto all the way down, dot, 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 all the way down, and we got down, and again, remember the network bits carry down, and we got down to the very end, and we had been counting binary all the way down, and we ended up at the bottom with all these being flipped to ones. Well, we know when we add that up, you add up the placeholder value where you have a 1. Well, in this case, it would be 1 plus 2 plus 3. Oh, whoa, I'm sorry. I'm looking at the wrong thing. That's how many binary digits we have. 1 plus 2 plus 4 plus 8 plus 16. Quick rule. When you have all ones and you want to know what it equals, you don't need to sit here and add all those up. It's always one less than the next column heading over. If you want to know what all those ones equal, it is one less than 128. The answer is 127. You want to check me on that? Let's check ourselves. Let's do something real easy. I want to know what those two binary digits equal. Remember, we wanted to know what all those as a string of ones equals in decimal. Well, let's just go real short. Let's go real small. Well, 1 plus 2 is 3. If you look at the next column heading, it's 4. I told you, a contiguous string of ones is always one less than the next column heading, 4. Let's check ourselves again. We want to know what 4 contiguous binary digits equals. Well, do we want to add up 1 plus 2 plus 4 plus 8? You can, or you can just go to the next column heading and subtract 1. It's 15. 8 plus 4 is 12. 13, 14, 15. There you go. So a nice little rule of thumb there. So what I also wanted to tell you is as you're counting down, and dot, 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 we've counted all the way down. We know we have to count 128 different binary lines here because, after all, 2 to the 7th power is 128. Starting at 0, you end up at 127. This minus 2 is the first one and the last one. When you're calculating how many usable IP addresses are on a subnet, it's always 2 less than, it's always 2 to the nth power, n being how many host bits you have, minus 2. Those minus 2s are the first one and the last one. This is known as your network identifier, network ID, and this is known as your broadcast. Okay? So, by definition, when all the host bits are set to 0, that is the network ID of that subnet. It's identifier, the subnet identifier. And it's actually what the route looks like in a routing table. The route in a routing table for this subnet is in fact the net ID with the respective subnet attached to it. The respective net mask. So the net ID with a /25 is actually the route that you would see in a routing table of a router. Now, the last one is the broadcast address. If you ever sent a ping packet to the broadcast address, which would be 123.246.10.127, it is supposed to go out to every computer on that subnet. All right? But these are not usable for numbering your computers and your routers. You cannot use the first one and you cannot use the last one traditionally. Okay? So this subnet that we've been talking about is in fact known as, if you calculate the net ID back to decimal using the respective net mask, you come up with 123.246.10.0, because look at this, when you convert this full, so when you convert it back to decimal, you've got to consider the full 8 bits, because after all, the full 8-bit string is represented in one decimal number field. All right? And so hopefully it's becoming clear to you now that you really can't see the delineation inside of the decimal number between network and host bit unless you break it out into binary and you see that it lies right there. All right? It's easy to see the delineator between network and host when it's on what's known as a byte or octet boundary, if it's there. But when it's inside of here, which is the case of a /25, it only becomes very clear when you break it out into binary and you see that's where the line is. Okay? So this is sufficient at 126 to number our LAN 1 on the far left side of our diagram. That's 101 IP addresses that are needed, and we can use that for over there. So we know now that we can use 123.246.10.0/25 for this first LAN that we need to number. That has plenty of address space. It's got 126 addresses. One of them will be used for the router, so we have 125 left for the subnet. Now, we need to get a couple more subnets. So we know we've already used this first binary digit of this fourth octet for this subnet. So we can't use that. So let's go to the next one, 1. Well, if we carry down a /25, we're going to have one other subnet of 125 addresses, which would be great for over here, but we will have used our entire address space. Think about it. In this first one, in this placeholder, in this position here, if you use a 0 and a 1, where do you go from there? There's no other binary value. So you've used up the entire /24 by cutting it into 2 parts. Whenever you subnet a prefix further, if you only slide the boundary over 1 bit, you've cut that into 2 logical halves. When you slide a 24 over, again, here's the dot for that. So this was our natural /24 boundary. When we slide that over to the /25 boundary, you have two possible binary digits that can flip in that 25th bit position of the 32-bit IPv4 address. So if we stop there and we assign another /25 of value 1 here in this bit space, you can only have one more subnet, and you need 2. You need 1 for the router and 1 for the LAN. Now, we're not going to talk about IP unnumbered at the moment for this point-to-point link. We're just going to go on actually assigning IP addresses to subnets, okay? Look into that on your own. But, and this is a challenge that you'll face. You'll need to put subnets on various broadcast domains and various LANs and WAN links and things like that all over your network. So it's a great exercise. So again, you can't use a 25 on this one. So we need to slide it over 1 more. Okay, so we already used this one. Let's just say that one's done. This is .0/25, as we have assigned up there. It's already used for LAN 1. Let's try to get LAN 2 taken care of. So let's slide it over to this space, to this position. This would be known as a /26. Now, again, the rule is 2 to the nth power minus 2 equals how many usable addresses you have. Well, we've already, if we're sliding over to a /26, we now have 1, 2, 3, 4, 5, 6 bits left in our host field. 2 to the 6th power, again, counting with my fingers, starting with 2, 4, 8, 16, 32, 64. That's good. We get 64. So we get 64 minus 2 equals 62. We're going to use 1 for the router, so we're going to have 61. This is plenty for this LAN up here. So we're on track. So let's stay with the /26, and you will count those out as you did before. We already went through this. The first one being all zeros. This is the net ID. When you add up the placeholder values, if in fact there's a 1, which there's not, then you to compute this back to decimal over here, you have to calculate out, or you have to add up the entire 8 binary digits. And I just said there's no ones here, but over the whole field, to calculate that back up to this decimal representation for this octet, you've got to add up the entire 8 bits, including the 2 that are used for network and all the ones that are used for host. You've got to add up all those to recompute that decimal form of that last octet. So this is 128, there's no others. So this first position is 128/26, and that is the net ID. Remember, all host bits, when set to 0, is known as the network ID. So it's known as the net ID, but to get it back to its decimal form, I'm just reiterating, you have to add up all 8 bits. So that's 128. This is the network identifier for LAN 2. So we could then say that LAN 2 is 123.246.10.128/26. All right? So that's good. That's the subnet for that. And if you want to know what the dot, let's just say ... We've calculated all the way down ... And you carry down 1 and 0 all the way down for network bits. You know, those never change on this subnet. If we calculated this all the way down, you end up with this being the final binary string of all ones. And we know that the definition of all host bits on a subnet of all ones equals the broadcast address. So again, we also know the rule that if you want to know what the decimal equivalent of that is, it's always 1 less than the next column heading. So the next column heading is 64. Well, that means that's 63. But to calculate this back to the decimal form for that 4th octet, you've got to add up the whole 8. Well, we know this is 63 plus 128. Just real quick, 128 plus 63, 8, 9, 10, 11, 9, or 8, 9, that's 191. So 191 is our broadcast address. So if you're asked, what is the first usable address on this subnet? It's not the network ID, it's one after that. So 129 is the first usable. What's the last usable? ... It's 1 less than the broadcast, which would be 190. So the first usable on this subnet is 129. The last usable is 190. Okay? That takes care of that LAN. Let's take care of the point-to-point link between the router. So now we have used up a good bit of our address space to this point. We started with a /24, and we have used one whole /25 and a /26. The /25 started with that, and so we know this is .0/25 is LAN 1. Ooh, I'm scribbling. We know that 1, 0 with a boundary. Okay, let me put a boundary here. That's our /25 for that one. This is our /26 for this one. And we know that that was .128/26 for LAN 2. Now we need a subnet that's big enough to have 2 IP addresses, one for each router interface. So we know that we used up 1, 0, the whole thing. So now we need to go to, we can go to 0, 1 in this space, okay? Because this uses up, no we can't. 0, 1 is used up here because the first one is like this, The last one, dot, 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 is all these flipped on. Well, look at that. That 0 and 1, if I would have done that, that would have been an overlapping assignment. You don't ever want to do that. Okay? So the next one possible is going to be this uses up this, dot, 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 all the way down to that. So, but what we haven't used is 1, 1. Okay? So what we'll do is that will be our assignment for our next subnet, 1, 1. Now, we know that the rule is 2 to the nth power minus 2 gives us what we need here. So we're not going to talk about /31 address space right now, nor are we going to talk about IP unnumbered. We're actually going to try to allocate out a subnet that is a traditional type of a point-to-point link subnet, which is usually a /30. But let's just do the math. If it's a /30, that would lie right here. This would be the 30th bit, so /30. Because if we went over here, we'd have a 31, and then the last one is 32. An IP address is 32 bits long, so the 32 is at the very end. So a /30 is right here, which would leave us 0, 0. This is going to be real easy to count. 0, 1, 1, 0, and 1, 1. And so if we use a /30 all the way over here, that means that all this is network bits, and these are our host bits. We only have 2 host bits. So 2 to the second power minus 2 equals, so that's 2, 4. So this is 4 minus 2 equals 2. That's all we need. We need an IP address for the router interface there and an IP address for the router interface there. So a /30 is good enough. The first one is the network ID. And when adding this up all the way across, I'll draw the /30 a little bit higher than that. When you add these up, you have to, or again, you have to add up. I'm going to draw these a little bit smaller to make them in line. You have to add up all these zeros in here. Excuse me, all the ones all the way across to get the whole conversion back to decimal for that octet. Okay, so 128 plus 64 is 192. Dot 192 /30. This is for the WAN link. So we can say that our WAN link is 123.246.10.192/30. That's the WAN link right there. Okay? And then the broadcast is all ones, and then the 2 usables are the ones in the middle here. So 193, when we flip that bit to 1, and 194, and then 195 is the broadcast. And you probably saw in there that there was some address space that wasn't used because of all that network bits in the middle were set to zeros when allocating out that /30. There's still a good bit more address space that's available for other additional things. Not a whole lot, but there's some in there, okay? So I put this in a Microsoft Excel spreadsheet, and it calculates it out for me, and I actually made it where it shows all the binary bits, and when you flip bits, it calculates it out into decimal, and I keep track of all my address space that way. There's programs out there that do that for you, but I just did one myself because I got real comfortable with subnetting by doing that myself. So I hope this was really helpful, and I look forward to doing another video for y'all later.